We treat our modern devices like magic. You tap a piece of dark glass, and instantly, a video plays, or a message reaches the other side of the planet. We expect them to be flawless, invisible servants. But take away the network connection, and even the most powerful workstation on Earth is an isolated electronic hermit. Without a link to the outside world, you are back to physically moving data through floppy disks and USB drives. The real power only begins when a machine joins a society of other devices. We connect them to pool resources, share hardware like printers, and establish a single, centralized source of truth so every computer isn't an island of outdated information. But the exact second you plug everything together, you introduce a massive problem. Right now, your phone, your computer, and your neighbor's router are blasting data out millions of times a second. They are essentially screaming into the void, competing for the exact same airspace and copper wiring. It is absolute invisible chaos. That behind the scenes, a specific set of physical and logical rules ensures your signal survives that microscopic noise. The journey out of that chaos starts in the physical realm. In most office buildings, you'll find hundreds of feet of Ethernet cable running through the walls and ceilings. These cables use a solid copper core because solid copper transmits data well over long distances. But that efficiency comes with a structural trade-off. Solid copper is highly brittle. If you repeatedly bend, flex, or manipulate those rigid cables, the internal wire will stress and eventually snap, killing your signal entirely. If you took hundreds of those stiff cables from the ceiling and jammed them into your server equipment, any slight movement could break a wire. You'd quickly end up with an unmanageable, tangled mess that actively destroys your network's integrity. To protect the infrastructure, engineers use a patch panel. It acts as a permanent termination block. The long cables from the walls punch down into the back of the panel and are never moved again. Then, short, flexible cables connect the front to the actual network equipment, isolating permanent wiring from the wear and tear of daily changes. Physical order and cable integrity are the prerequisites for this entire system. Without them, no digital communication can even begin. Once the data safely navigates the patch panel, it flows into the network switch. Older network hubs used to just blindly duplicate incoming data and shout it out to every connected device, creating constant digital collisions. A modern switch is a self-learning machine. Every piece of network hardware has a unique physical identifier called a MAC address. When you plug in, the switch reads that code and builds a real-time, localized map of where every device is. If your computer pulls a file from a server, the switch creates a dedicated electrical lane. Nobody else sees that traffic, entirely eliminating collisions. But we aren't always tied down to physical cables. Wireless access points, or Wi-Fi, present a much steeper engineering challenge. Instead of giving you a dedicated private lane, radio waves operate in a shared, invisible airspace. Everyone in the office sits in the same room. If two phones transmit radio signals on the exact same frequency at the exact same millisecond, the waves interfere and corrupt the data. To survive this, Wi-Fi forces devices to listen before they shout. Your phone's microchip monitors ambient radio energy, waits for a microscopic gap, and only transmits its data when the airspace is clear. Whether you are routing electrical pulses down a dedicated copper wire or taking turns firing radio waves through the air, the network survives by enforcing strict traffic laws to prevent physical collisions. You can have a flawless physical path, but if the two devices at either end don't speak the exact same language, no communication occurs. This is where networking protocols step in. These are obsessive, strictly defined digital rulebooks. The heavy lifter of the internet is TCP, or Transmission Control Protocol. Its entire job is accuracy. If you need to send a massive file, TCP is like the postal service telling you to send a 1,000-page manuscript by putting exactly one numbered page in its own individual envelope. The receiver must send back digital receipts for what arrived. If envelope 2 gets lost, the receiver flags it, and the sender instantly generates a perfect copy to replace it before moving on. But sometimes speed matters more than perfection. If you are watching a live sports stream or making a video call, there is no time to wait for missing pieces. That's when devices use UDP. Instead of waiting for receipts, UDP acts like a t-shirt cannon, blasting data as fast as possible. If a frame drops, the stream just moves on to the next one, so the live action doesn't freeze. By layering these protocols, our devices deploy the exact right strategy for the moment, demanding meticulous, verified delivery for a bank transfer, or choosing raw, unfiltered speed for a live broadcast. Looking at the multi-protocol synergy on the right side of this diagram, you can see how all of these distinct rules work simultaneously. When you click Send on an email, these protocols stack together through a process called encapsulation, acting a lot like Russian nesting dolls. Your email application formats the message perfectly. It hands the email down to TCP, which negotiates a handshake with the receiving server, chops the message into numbered packets, and pushes it down to the physical hardware, which converts that data into raw electrical impulses. Those impulses shoot down the solid in-wall copper wiring, safely navigate the permanent patch panel, and flow into the network switch. The switch reads the physical MAC address, instantly maps a dedicated lane, and fires your email out into the wider internet. This intricate sequence of physical physics and digital logic executes flawlessly in the fraction of a second it takes you to blink. Instead of feeling annoyed the next time a web page takes an extra second to load, you might just find yourself marveling that this system of organized chaos actually works at all. We imagine the internet as an invisible abstraction, but dive beneath the floorboards of any data center and you find a massive mechanical reality. Every moment spent online depends on a tangible mechanical connection to the physical world. The global internet is simply a worldwide collection of interconnected local networks, cooperating to exchange data over actual hardware. Every device we use, from the laptop on your desk to the smartphone in your pocket, right down to smart cars and hospital heart monitors, relies entirely on this continuous chain of physical equipment to function. To truly understand how networks communicate, IT professionals have to look past the user interface and strip away the software completely. We have to examine the raw base data being transmitted, the physical media carrying it, and the real-world obstacles that slow it down. Troubleshooting the internet requires treating it as a rigid mechanical system, governed by the laws of physics, rather than a theoretical void. At the very bottom of this mechanical system is the absolute base unit of digital logic, the binary digit, or bit. A bit is not a conceptual number. It is a precise measurement of one of two discrete physical states, an electrical charge that is either on or off, a 1 or a 0. When you type a character, computers use standard binary codes, like ASCII, to group these individual bits into 8-bit sequences called bytes. If we break those inputs apart, a capital A becomes the exact sequence 01000001, and a 9 becomes 00111101. This diagram illustrates what happens next. To cross a network, bits must be converted into physical signals. The first method relies on copper wire, translating data into pulses of electricity sent as jagged signals from machine to machine. The second method requires fiber optic cable, converting electrical signals into pulses of light traveling down a central optical tube. Finally, devices can translate data into radio waves, broadcasting the signal directly through the air. A single message will rarely stay in one format. As it travels from source to destination, the signal is converted multiple times to cross different types of media. No matter how sophisticated a software application looks on your screen, all global data transmission strips down to these three physical phenomena. Those physical connections scale outward, starting with the simplest configurations. A small office or home office network, a SOHO, might wire together just a laptop, a printer, and a single router. Contrast that with the massive infrastructure of a corporate campus. Here, physical lines branch out, connecting thousands of individual hosts into a single unified grid. This graphic demonstrates scaling up further. The World Wide Web is millions of local grids wired together globally, and the endpoints of this network have evolved beyond desktop computers, extending directly to the mobile devices in our hands. Today, a smartwatch tracking your pulse or smart glasses projecting a display push physical data onto the network. Inside the home, everyday refrigerators, smart TVs, and gaming consoles are wired to centralized servers. Outside, industrial RFID tags, agricultural sensors in the soil, and mechanical actuators exchange data to automate real-world logistics. The global internet consists of the total physical infrastructure built to route electronic signals between this endless variety of edge devices worldwide. Getting signals across the planet requires capacity. Bandwidth is the theoretical maximum amount of data a medium can carry in a given time frame. This capacity is strictly limited by the physical properties of the medium and the governing laws of physics. We measure this theoretical pipeline in bits per second, scaling from a few thousand kilobits all the way up to billions of gigabits per second. But theoretical capacity is rarely what you experience. The actual, measured transfer of bits over a specific period is called throughput. Throughput is always lower than bandwidth. Different data types and file sizes ensure the physical flow is never perfectly smooth. The main culprit is latency. Every time a packet hits a physical barrier, like a router, it takes time to process, causing a traffic jam. Throughput is reduced even further because your network pipe isn't just carrying your files. A portion of that bandwidth is always consumed by network control messages and error correction traffic just to keep the system running. This creates a hard physical limit. In any multi-segment network, total throughput can never be faster than the slowest single link in the entire path. High bandwidth provides raw capacity, but network engineers must calculate for latency and physical bottlenecks to find the actual speed a user will experience. Let's trace a single piece of data through this physical gauntlet. Imagine an agricultural soil moisture sensor. The dirt dries out, drops below an acceptable level, and triggers an alert. Immediately, the sensor's processor translates that environmental change into a binary state, a bit. For its first physical hop, the device broadcasts that bit as a radio wave, sending it to a local monitoring station. The station receives the wave, translates it into an electrical pulse, and pushes it down a copper wire toward the local internet service provider. At the ISP, that electrical signal is converted into a pulse of light, injected into a high-bandwidth fiber optic backbone to instantly cross the country. The fiber provides enormous capacity, but the final throughput is ultimately dictated by the processing delays of the routers it hits before logging into a centralized database. Network engineering involves mastering the physical journey of binary states across varied media to bridge our digital and physical worlds.